Hello. So today in this video we'll be discussing angular momentum. Now, angular momentum is the momentum of a rotating object, and it can be found by the product of inertia and angular velocity, where inertia is the measure of resistance of an object to changing angular speed. Angular momentum is determined by an object's mass, velocity, and the radius. So for today's problem, we're going to be looking at a gymnast that will be doing a flip. The gymnast is going to start with his hands up, so we'll start drawing that picture. So let's go. Here's their head. They're leaning a little bit forward, and their feet are like this. And then let's just say their arms are somewhere up here. Their feet are kind of short. Let's do longer feet. So this gymnast is starting to do a flip, and their area of rotation is going to be about right there. Let's just say that's their area of rotation. That's the center of mass, because that's what they're going to be rotating about. And draw to do how their body's going to rotate. So that's where they're going to be starting at. And we're trying to find, when they're at their peak, we're trying to find that angular velocity. So they're going to be upside down. That's their chest, their knees are going up, and then their legs are going back down, and then their arms are somewhere here. So that is their secondary position. This will be position 1. This will be position 2. Their angle axis of rotation in the middle, so somewhere like that. And we'll say that's the axis of rotation. And then we'll draw that same circle, going from the top to the bottom of the rotation. So what we are given is that they're given is their mass equals 50 kilograms. Their length, which is from here, we're gonna go from the tip, from the how they have their hands to the bottom. We'll say this part is L. We'll say that L equals 1.6 meters. And then they have angular velocity here. And we'll say that their angular velocity is, let's go with 11 radians per second. So that's their at position 1. For position 2, this length is half of their initial length. So length divided by 2. Note that angular momentum is a vector. It can be found by using the right-hand rule. So what we're looking for, what we're trying to find, is angular velocity at position 2. This position, when they're at the very top. What is their angular velocity when they're completely tucked in and their overall length is half of what was initially? So one way to do this is to say that the sum of the initial angular momentum equals the sum of their at position 2. Angular momentum at position 2. So we know that angular momentum is inertia times angular velocity. So then we can go inertia at position 1, angular velocity at position 1 must equal inertia at position 2 multiplied by angular velocity at position 2. So for position 1, they look like they're like a rod, right? So the inertia for a rod equals 1 over 12 ml squared. Okay, so that's inertia for a rod. Now for position 2, their inertia looks like a sphere, because they're kind of balled up. I probably stretched them out a little bit. In reality, they'd be really tucked in, probably with their knees way closer to their head, and their feet wouldn't be out here. They'd be more like out here. I'll leave it like this for now, because all we really care about is that how much the length is smaller. So if we're using the inertia of a sphere for the second one, the inertia of a sphere, let's put it over here, I equal 2/5 mr squared. Note that over here we have the length over here we have the radius. So we got to find what the radius is. So the radius is half of our length over here already. So, and our length is already L divided by 2. So half of that, R, equals L divided by 4. So that's what we're going to plug in here to find that inertia. We know what angular velocity of position 1 is, and we're trying to find angular velocity of position 2. So what we can say is we can rewrite this and say that angular velocity, I should put vectors here, because these are vectors, at position 2 equals inertia of position 1 times angular velocity of position 1 divided by inertia 2. Now, if we plug in inertia and angular velocity for those, let's just plug in the inertia for now. So we can say our inertia initially was 1 over 12 ml squared times angular velocity position 1, and then we'll have inertia 2, and inertia 2 is this one. So I'll take the 2 over here, I'll put it there. That 5, I'll just bring it to the top. And then I'll go mass, and then instead of just writing radius squared, I know my radius is L over 4, so I'll go L over 4 squared. So I'm going to quickly work this out to the side right here. I'll say L over 4 squared is L squared over 16. And then rewriting this all, I can say, so this will be 5 ml squared rho initial divided by 12 times 2 is 24 m, and then I'll have L squared from here, and then this 16 will just go up here, so I'll go ahead and write it right there for now. Okay, and there's a few things we can notice that cancel out. We see that the mass cancels out. We see that the length squared cancels out. And now we're just left with some algebra and then plugging in our initial angular velocity. All right, so 16 times 5 is 80 over 24. And then our initial velocity was 11 radians per second. So in the end, our angular velocity turns out to be 36.7 radians per second. And so that's how we're able to find their position at this point. So this angular velocity would be right there. So at that point, when they're at the very top, when they're completely tucked in, their angular velocity would be 36.7 radians per second. If they were able to decrease their size in half from when they initially launched. And obviously our angular velocity that we're using is the instantaneous velocity right before their feet leave the ground. That's how we're able to use the angular momentum and the conservation of angular momentum to find our angular velocity at position 2. Thank you.